Mubot, what are you doing? He's saying teaching class. Brian went and got, looks like some cookie dough. It's a Quest bar right there. Oh, man, it's good stuff. Grab a little snack between class. Good to see you, Tiffany, Olivia, Kayla, Snea, good to see you here. Trevor, good to see you here. Chapter 15, I know, right? So we're going to start up right here. I think we got 3 questions ready. We'll do some Canvas content, and then we will do some Chapter 15 quiz, and we're going to do some harmonic regression, some woo, 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 coming up soon here. So let me get the Canvas content going. I went and grabbed a quick snack between class right there. Man, those Quest protein bars, whew, some good stuff. Anyone else had a Quest protein bar besides Brian? Who's my people in the chat right now ever had a Quest protein bar? They got see, someone who's really into nutrition be like, what you doing eating some sugar? I think it's used as Splenda or something. Or stevia. Use stevia, I think, is in it. Is that bad for you? I'm sadly addicted. Good quick snack. My brain broke. Loading up some stuff. They got birthday cake. They got cookie dough, double chocolate fudge, all that good stuff. So much good stuff. All that great stuff. By great, I mean maybe a little bit bad for you. And we're loading up right here. Confidence intervals. Canvas content. Oh, wait. Oh, it's due next Monday? Cool. Let's do it, though. Canvas content. Let's do 3 versions of it. Quest bars are pretty good for you. They have a lot of fiber too. Oh, that's awesome. Yeah, they do, don't they? The airlines question, you bet. I heated it up in the oven. I just went and heated it up. All right. I'm going to disappear. You take over, man. You teach this class. Brian.
Brian.
Where am I?
There I am. Brian's gonna eat real quick. He'll be back in 20 seconds. I'm teaching though.
You bet. Go away, man. Okay. Great answers in the chat. Great job, people right there. As Brian finishes off his snack right there. Now I'm going to get my coffee. Got my Doctor mug coffee. This is very true. William Gossett. So I guess we could put it on the test like this. William Gossett. We talked about Mr. T today. You'll get to hear this in the afternoon class. We call it the T distribution. Mr. T comes in, smashes it down. Newbot was teaching away. He does an excellent job teaching when I bring him in here to teach. But William Gossett right here, an employee at the Guinness Beer Factory, made it. And we also got to see the plaque. Did I remove the plaque from the screen? Do I still have that screenshot up? Yeah, I do. There it is right there. William Seeley Gossett, chief brewer, and created the student tea distribution. So he published under the pseudonym Student and called it the tea distribution. And it's basically the what distribution? It's basically the this distribution. Basically, the numbers are going to be a little bit different. It's basically the this distribution. 100 points for everyone participating right here. It's basically the what? Oh, definitely, Brianna. You bet. We got you bet, Brianna. We'll do some chapter 14 coming up here soon because that is due tomorrow night. It's basically the normal. Basically the normal, which is chapter 14. Yeah. So we're doing some conference roll stuff right now, and then we'll do some more Canvas content coming up, or some more by Pearson coming up here soon. But smash down, exactly. So this is true right here. When we do a conference roll for the mean, which of the following distribution to determine the number of standard deviations needed for our confidence? Yeah, I mean, should we call standard? When we do a conference roll for the mean, who remembers our saying from class? Mr. T is this if you're doing drugs. The nutrition lab, you bet. Yep, we'll do it here in a little bit. So the T distribution, right? So the T has with it degrees of freedom, and Mr. T is mean if you're doing drugs. So he's a super nice guy. You gotta watch those 80s commercials. I'd play it on here. Oh man. Okay, give me 2 seconds. I can only play like a second of this. Mr. T is like one of my 80s icons. We gotta be careful. This is how we get copyright claimed on this channel. Yes! Oh man, this is so... It's so low grade. And Mr. T did exactly. So here it is right here. This what's so great about this is he literally takes the glass of milk in his hands and he smashes it. Oh, we're gonna copyright. I love it. I love it. It's so cool. Oh man. He's like, if you're doing drugs, I'm not happy with you. He's like, don't do drugs. I'm gonna tell you. He's like, okay. And the best part at the end is he smiles. He's like, don't do drugs, okay? Don't hit us with a copyright claim, whoever owns this video with 75,000 views. But don't do drugs. So Mr. T is unhappy with you. What are we learning right here? What to remember? If we're doing means, we're using what distribution? If we're doing means, we're using what distributions? If we're doing means, why are we keeping repeating this? If we're doing means stuff, we're using what distribution? If we're doing means, keep saying it to me, we're using what distribution? You see it on the screen. If you're doing means, which it says right constant for the means, you're using what distribution? They can see it in their YouTube analytics. Whoever owns the right set video could see it on their analytics, like someone, depending on how much of it I show. And if I do it transformatively, which I hope I did, they shouldn't be able to copyright claim me. And then they could put ads on this video. So if this office hours has ads on it, which I don't put ads on office hours, it'd be because we got copyright claimed. So if you see T, it's for means. Does everyone see the connection right here? This is what we're learning, is that if we see T right here, it's for means. So why is this not a T interval? Why is this one not a T interval? Just repeat to me, why is this one not a T interval? Because this interval is for whats. It's not for means. This interval is trying to estimate the true what. Why is this one not a T interval? Why is this one not a T interval? Because we're using p hat to estimate the true proportion. So we're trying to estimate the true proportion using p hat. This one is trying to estimate the true mean from using the sample mean. So this is a confidence interval to estimate the true mean from the sample mean. Means T, Mr. T mean, if you're doing drugs. This one is not a T interval. This one, because you're using P right there. Proportions, categorical, Kayla, great job right there. So we don't want to just ace the Canvas content. We want to know why, because you can memorize these answers, but remember, since we're doing the mean right here, we're going to use the T. We haven't even talked about chi-squared. Really, the answers are these three, but we haven't even talked about chi-squared yet. Talk about that section of this chapter. Decreasing the sample size will make the margin of error smaller. So let's look at the sample size right here. We have an equation. If I were to decrease the sample size right here in this equation, what would happen to the margin of error? Like you have one interval that uses, so here's the margin of error. Margin of error is equal to the T statistic. We'll just write T right there. S over square root of N. So if I were to use a sample size of 1 or like 1,000,000, if you use a smaller sample size, the margin of error will get wider. And think theoretically right here, if you sample less people, your margin of error, which is your uncertainty, would get wider. If you sample less people, so if you were to make this smaller right here, your margin of error would get wider. So now you're dividing by a smaller number, so the margin of error will get wider. Smaller sample size means wider margin of error. Bigger, because you're more uncertain. You just think theoretically, if you talk to less people, you would have more uncertainty. So mathematically, if you have a bigger sample, you're dividing by a bigger number. So dividing by numbers makes things smaller. It would make the margin of error smaller. So mathematically, when the sample size, which is n right here, and n in that equation right there, remember the margin of error is everything after the plus or minus. So I'm just only using the margin of error right here, everything after the plus or minus. If we have a larger sample size, we would have less uncertainty or smaller margin of error. If we have a smaller sample size, we'd have more margin of error. So decreasing the sample size will make the margin of error a smaller value. Decreasing the sample size will make the margin of error bigger. A confidence interval is made from a blank to estimate the truth for a... Oh, I love this one. Is it A, B, C, or D? I want you to answer this. This is a huge, just fundamental thing in statistics. Is it A, B, C, or D? Great job, Tiffany. Already following along. We'll do another version of this in a moment. Is it A, B, C, or D. This is huge fundamental statistics. Great job right there, Olivia. It's made from a sample. And you can see that in the formulas to estimate the truth for a population. In the formulas you're seeing on the screen right here, it literally says, if you look, this is made from the sample proportion, and we're trying to estimate the true proportion. So what value, 500-point question in the chat, what notation value are we trying to estimate with this interval? What notation value are we trying to estimate with this interval right here? In notation, I am trying to estimate what? 500 points in the chat. Huge bonus points for office hours. What notation value am I trying to estimate? I have a sample mean. I want in notation. What we're trying to estimate is what with this interval? We have the sample mean. Well, that's what we have as our estimate. So what are we trying to estimate? You're close, Kayla. So we have the sample mean as our estimate. We're trying to estimate what? Not the standard error. Not T. Not N. Oh, that's a good question. We're trying to estimate, think of cows. I'll give it 10 seconds. Think of cows. The cows. Well, here's the real another quick hint. In this one, we have the sample proportion to estimate the true proportion. This one, we have the sample mean trying to estimate the true mean. I'm going to throw out the 500 points. Good guesses, everybody. Giving you the points right there. Boom, Carson got it, and Kayla got it at the last moment with that mu. We're trying to estimate mu, the true mean. Does that make sense? Like, what's your best guess of the true mean? The sample mean. What's your best guess of the true proportion? The sample proportion. Does this make sense theoretically right here? So I guess about 25% of students, my best guess of the truth, 25% own a dog, because it came from the sample. I talked to a bunch of students, and the average GPA was 3.2. So my best guess of the true mean GPA of students is 3.2, because that's the sample mean. So this literally goes to the question we're doing right here, that we go from a sample to make estimates of truth for the population. And the theory is the hardest questions on the test, because some of the questions are just plug and play. So yeah, margin of error. I love these sorts of questions. Who here can tell me how I would find the margin of error? Like mathematically, whenever I find a margin of error, let's draw our interval right here. The interval says it goes from 64. I'm in highlighter right now. The margin of error is what for this interval? You got it, Kayla. Kayla's explaining it. Great job, Kayla, right there. Kayla is saying it's half the interval. So whenever you think of the margin of error, sometimes we give decimals, which makes the question a lot less fun, but you're really just asking yourself, what is half the length of the interval? Like, just go to the interval and then say, what is half of this length? So to find this, you would just find how long the interval is. So let's go. Kayla might already have the answer. Kayla, just amazing work solving these things really quickly. I love it. So we're going to go right here. We're going to find the length of the interval. How long is the interval? Is upper minus lower. So 72.9 minus 64.6, and then divide by 2. You got it. So to practice this, I like to ask the following questions. We should get 100. We should. I'm worried. Always a little worried. 10 out of 10. Love it. Let me ask you this question. If I tell you I will arrive to the party, let's say, between 5 and 6, what is the margin of error? Be very careful. A lot of people go really quickly and they get it wrong. I say I'm going to arrive to the party between 5 and 6. What is my margin of error? Be careful. And remember, it's half the length of the interval. I say I'll get to the party between 5 and 6. Kayla just aced that. Like, boom, 15 minutes office hours. You got it, 30 minutes. Yeah, half the length of the interval. 5 to 6, 30 minutes. So I'm somewhere 5:30 plus or minus 30 minutes. Kayla, 15 minutes in office hours. Another 100 point you right there. 15 minutes in office hours. Aced it right there. Aced the quiz. Great job, Brianna. Also, let's do it. Is there so few questions? We're going to do one more version of this. We might go a little bit quickly because we might get some repeat questions. And then we're going to jump into the next question, I think was a quiz question. And then Snea, your questions next. Thank you to everybody. An employee at the Guinness Beer Factory. True, we did this one. The T distribution for means. We did that one. Comps are made from a sample to estimate the truth for a population. The success failure condition for proportions requires at most 10 or at least 10. Might do one more version of this. Does it B? At least 10 successes, at least 10 failures. That's success focus. Remember, these questions are on the test. The only way to change the margin of error is to change the sample size. What else could you change? To change the margin of error in this interval, we could also change the what? To change the margin of error in an interval, you could also change the what? You could change sample size, the confidence level. It's false. Great job right there, Brianna and Olivia. You could also change your level of confidence because that is part of the margin of error. And we're showing for two different formulas right now that the T right here controls the confidence, also the Z for this interval, T versus Z interval, depending if we're doing means or proportions. So that's very false right there. Let's do one more version. That should be another 10 out of 10. This is where you get it down, where you just like know the answers and know the theory. One more version of the quiz, and then we're doing some Mop Pearson. We're seeing everything up. New question. No matter what the shape of the parent population is, as long as our sample size is 10 or greater, we can conclude that the sampling distribution of the sample mean is approximately normally distributed. False. Because what if it's very, very what? What if it's extremely what? If it's extremely, extremely this. So what if it's very, very what? I'm trying to go to the conditions on here. What if it's very, very what? Skewed, exactly. You need a larger N. So if it's very skewed, you'd need a much larger N than 10. So if your sample size was 10, it might not be large enough. So that's wrong right there. When we do a confidence interval for the mean, we'll be using which of the distributions? Remember, Mr. T is mean if you're doing drugs. So there's your T interval. Go from sample to population. We've done that one a lot. Decreasing the sample size will make we did this one earlier. This is false. It'll make it larger, less sample. The only way to change the margin of error is to change sample size. This is false. Confidence level. Check. If you're seeing me do these quickly, it's because we did these and explained the theory. Let's give one more version. I know we've done this a lot right now. We're just going to see if we have one more version with one more new question. And just acing this. Look at those times right there. Yes. Practice, practice, practice. Know the answers. Know how to solve them. Let's do one more version, and we're hopping here to my Pearson. I just want to have a few more new questions. Really? You going to load? You going to do it? Oh, we're on it? Okay, here we go. Ooh, we got a new one. Which of the following would you not use to check the nearly normal? Ooh, I love this one. A, B, C, or D. This is a great question. A lot of people get this wrong. Which of these would you not use? A bar chart, because bar charts are for what sort of data? Great job. I'll answer it, Olivia. It's a great answer. Bar charts are for categorical. So we're not doing categorical data right here. Remember, bar charts are for categorical. So the nearly normal is a quantitative. So bar charts would not be used. You could use histograms, normal quantile plots. For univariate, great answer right there, Brianna. Univariate quantitative, univariate categorical. You see that up there at the top. Just one categorical variable would be bar charts. So since we're doing a quantitative distribution, we can't use bar charts. That's a good question. Love that one. A lot of people get that one wrong. Employee at Guinness Beer, that's very true. William Gossett, decreasing the sample size will make the margin of error larger, not smaller. This one right here we did earlier. Please check out the solve for this. The margin of error is half the length of the interval. We did that one a little bit earlier. And we need at least 10 successes, at least 10 failures. Great stuff right there. Really good practice. If you notice, we're speeding up as we do these, which is really great. Do we got another 10? Where did we misclick? Where did we misclick? Oh, did it change the interval? Well, good. That's a good way to end this, right? The margin of error is half the length of the interval. This question likes to change what the answer is. So we're going to take upper minus lower divided by 2. Round up. A little plus or minus there to make sure you get it. We should. I think, Tiffany, we'll be doing that here in a little bit. You bet. We're probably going to do a lot of 14/15, and we're going to hop in here. I think the next question on the docket is... Let me hop here to the main screen, and we're going to go to the next question. Hope people got some 100s and practicing the concepts. Olivia says, Chapter 15 quiz was the next question from Olivia right there. And I have the abnormalities question, Olivia says. The abnormalities question. And then I think we have Snea's. And then I think we have Brianna's. And then Tiffany's. So here, let me put this in the chat. You ready? Snea next. Then Brianna. And then Tiffany. Remind me of this order if I forget it. Remind me of this order if I forget it. So we can loop back around. Here we go. Let me get my Pearson up and going. We have more than enough time. We will get to all these. But if you have a question, put it in the chat so we don't forget. And hopefully I didn't miss anyone's questions. If you have a question, drop it in the chat so I can see it and we can put in the order. So we're going to do the abnormalities question from chapter 14, I believe. Abnormalities question. We're going to do some T distribution. My Pearson's being a little bit slow sometimes. T distribution. Abnormalities. Loading up preview. No. Replace questions. Here we go. If I do a preview, it doesn't show me every question. Okay. Flight question, Trevor. Awesome. I'm going to add yours, Trevor, right here. So we got you in the order, Trevor. I want to make it so it appears on the side of the screen. There's things I need to create that I just got to create some stuff. Oh, I just saw the flight question. There's two. Can you put there's two flight questions, Trevor. Can you put a good part of it on here? Because there's two flight questions. So if you can put a good portion of it, or like show me the start of it. Where's the congenital abnormalities? I've done it before. Olivia, which chapter is on the homework or the quiz? I just looked through all this and I don't see the congenital abnormalities. We did it a little while ago. Psychology. I'm flipping through right now. We'll try to find it. Am I wrong? Is it not chapter? Oh wait, no, that's pulse rates. Where is it at? Quiz chapter 15. Oh, 15. Oh, chapter 15. Let's do it. I was on 14. Sorry, my mistake. That's why. Chapter 15 quiz. We're doing some hypothesis testing now. Get ready for hypothesis testing. This will be a new thing. We'll be covering it next week. And so don't worry. So it doesn't matter. But Rock.
It doesn't matter.
It's gonna be similar to what we're doing, but it's gonna be a little bit different. So this will be new concepts if you haven't heard of hypothesis testing, but people are getting ahead. I love it. I absolutely love it. Because getting a head start's really going to help on these concepts. I might do this a little quickly. And then we got this. Let's go check this out. Here we go. Doing Congenital Abnormalities, Chapter 15, Stat 201. Let's check it out. Okay. So this is hypothesis testing. Now, every time we do a hypothesis test, we will always have something called this. I need a 4-letter word in the chat. I'm not going to use yellow. We will always have a this to start out. What is this called? Especially with this little thing right here, what is this called? Does anyone know what that's called? You see a bunch of them over here. And they all have an equals sign. They all say it's equal to something. So very important to know whenever you do a question. This is called the what hypothesis. That's not the right answer. The null hypothesis. Great job, Olivia, right there. That's the null hypothesis. And then you'll have an alternative hypothesis. The null always has the equal sign. Oh, Olivia, you are just on fire right there. The null always has the equal sign. Good way to tell whenever you get to a belief. Sam, another points right there. Great job, Sam. So we're going to start out believing something when we do this test right here. Well, let's mark our notation to start right here. It was generally believed, almost like that's our starting belief, and we'll call this mu naught. Oh, that's p naught. I gotta change my notation because it's a proportion. This is the hypothesized true proportion. In notation, p naught, because remember, p is the true proportion. It is categorical. Great job, Olivia. Because we're saying, does a baby have a congenital abnormality or does it not have a congenital abnormality? So p being the true proportion, p naught is the hypothesized true proportion. And so when we write this right here, we would write, if we had to write this by hand, that the true proportion is equal to some hypothesized true proportion. So this right here will be replaced with whatever value, 7%, and that should give a hint. We've now narrowed it down to a few answers. Now, the big question becomes, how do we know what the sign of the alternative is? So how would we pick between this one, or this one, which are the three alternatives? The alternative hypothesis will either be the true proportion is less than, greater than, you won't write all of these, or not equal to 0.07. The only thing that changes between this is the sign. When you rewrite this, that's a good thing to know. The only thing that's going to change is the sign. Does that make sense? You're only going to change the sign. And how would you know which the sign to use? The problem will tell you what we're testing. So is there evidence the risk has increased? I can't draw. Is there evidence the risk has increased? What do you think we should use as a sign if we're asking, is there evidence the risk has? Yes, Olivia, you got it right there. So that narrows it down right there. And the reason we're picking this sign right here is because, so we just wrote it out. We're saying The true proportion is believed to be this currently. We believe that the true proportion of congenital abnormalities is 7%. We're looking for evidence. Always say that with your alternative, like I'm looking for evidence that the true proportion of congenital abnormalities is greater than 7%. So that's got it right there. We are doing this test, and the ones we're doing, we're just going to select. We've written it, and the answer is this one. So let's clear our screen and go to the next parts. Is it a random sample? You know what's going to happen right here. Livy's saying it's met. I believe so. Randomly sampled. The independence, which is basically random. Less than 10% of the population was sampled. And then the success failure condition would be found by doing P0, because we're assuming that that's the truth, times the sample size of 365, and that's NP0, which is greater than 10. And then we could do NQ0. Q0 is 1 minus P0. And we go right here, and that's NQ0. So both NP0 and NQ0 are both greater than or equal to 10. Now this is where this problem jumps really quickly to a later part. The problem says find the p-value. That's a lot of steps. To find the p-value, we must first find the z-statistic. The z-statistic will not be used for confidence intervals. This is not a confidence interval problem. This is finding a statistical test, and we haven't done this chapter yet, but follow along and ask questions if you have them, especially if you're working on the homework right now. To find the p-value, you must first find the z. Z will be found via the following equation. Z is equal to p hat minus p0 over p0 q0 over n square root. So the question becomes, what is p hat? And so what is p hat up here? Do you see what p hat is? P hat is going to be x over n. So that's the number of successes out of the number of samples. So 32.65, 32 out of 365, less than 10%. So 0.08767. That's p hat. P hat is equal to 0.08767. Exactly. Great job, Olivia. Thank you so much. First, find the z. You got it. And so we're going to plug that in. I'm going to try to write nice and small. I might have to disappear. 0.08767. We already know what P0 is. P0 is this. That's the hypothesized true proportion. And we're just going to see how far away it is from this. And then on the bottom, you have to use P0 down here. P0 is this. Q0 is the complement, which means it adds to 1. So these two right here add up to 1, those two numbers. And then we divide by the sample size of 365. And when we solve this, which we will in a second right here, we will get the z-statistic, which is not the answer. Z is not the answer. That's just how many standard deviations that is away. Good, didn't break anything. 0.07 times 0.93 divided by 365, square root. Got that right there. 0.08767 minus 0.07. That's the distance up top. Divide by the standard deviation. It's called standard deviations time. 1.323. 1.323. Oh my gosh. Gotta get used to Epic Pen. 1.323. Now here's the thing. We're doing a greater than test. And the p-value for this is going to be close to, I'm estimating it. The p-value for this is going to be close to 3 decimals. I could maybe get it. That's whoops, need my 0. That's a guess. But where do we need to go here? We need to go to Mr. David M. Lane to confirm our answer. So, we're going to David M. Lane to confirm the answer right now. And so let's go check this out right here. I'm going to clear the screen. Remember, that is the z-score, 1.323. And I'll show you why I was able to guess a decent guess at that. Which way are we going to shade the curve? How do we know, Olivia, how do we know which way to shade the curve? How would you know when shading the curve right here to shade above the number, below the number, or on both sides of the curve? How would you know to shade this right here? How would you know which way to shade the curve? And I'll put the correct shading on the curve. How would you know to shade like this? How would you know to shade like this right here? How would you know that? How would you know I got to shade to the right of that number? How would you pick that? Because remember, there were 3 options. I could shade below the number, I could shade above the number, I could shade both sides of the curve. And why would I pick to shade above? What did we decide early on that is going to tell us we need to shade above when we choose where to shade on the z-score? How do we choose that? Depending on and look at it points to the right, so we shade to the right. If we had picked the less than, we'd shade to the left. If we had picked the does not equals, we'd shade both sides of it because that goes to both sides. So when you look at this right here, if you do the greater than alternative, you shade to the right. If you do the less alternative, you shade to the left. If you do the does not equals alternative, you shade both sides, which is double this one right here. Now, I was able to guesstimate this because I know the z-score for a 98% or 80% confidence interval is this. I guess it rounds up, but 6 right there. Really? Sure, whatever. But that is our number, and it's 9.3 or 0.093. There we go. So this is a one-tailed test, exactly. This is a one-tailed test. Great answers right there in the chat. It's a one-tailed test, not a two-tailed. The two-tailed test is the does not equals test. Olivia, good afternoon. Mohammed, we're going to be doing some, right after this, we're doing some 475, doing some harmonic regression. The p-value is the chance, the probability. P-values are probability of observing our results or results more extreme occurring by random chance variation, given that the truth is 7%. So the p-value is the probability of observing this many or more congenital abnormalities in a random sample of 365 if 7% is the truth. So we have that right there. Do you reject the null? Now, when the p-value is low, reject the null. The p-value needs to be lower than 0.05 unless stated otherwise. So when the p-value is low, reject the null. I want you to look at this p-value and answer, is this p-value low, yes or no? This is how you know to reject the null. Is that p-value? Let's put a scale right here. Olivia's got a great job, Olivia, right there. So we have right here the 0.05 standard, and we look at our p-value, and unless stated otherwise, this is low, and this is not low. So when the p-value is low, you say down here that you reject it. I'm blocking it. When it's down here, you say you reject it, and people a lot of times up here say fail to reject. That's just the old way of saying it. Okay. To just be like, so you did this, Brian? I failed to go to the mall today. You either reject or fail to reject. So translate, I failed to go to the mall today. Translate, I failed to go to the mall today. Translate that. Translate, I failed. Here, all I do, we got a list going, Mohammed. So translate Brian's weird statistical way of talking, I failed to go to the mall today. If I say I failed to go to the mall today, you'd say, oh, well, this right here, Brian, you did this. If I say I failed to go to the mall today, what am I saying? No, like you say, how'd your day go, Brian? I say, oh, I failed to go to the mall today. I failed to go to the mall today. You say, well, then you mean this? If I say I failed to go to the mall today. Did you make steak for dinner, Brian? I failed to make steak for dinner. What am I saying? It's weird to say fail to reject. You'll see that a lot in statistical wording. What are you saying if you say I failed to do this? Just translate I failed to do this. What does that basically mean? I failed to go to the mall today. I failed to make steak for dinner. It did not. Great job, Muhammad, right there. I did not go to the mall today. Does that make sense? You either do something or you do not do something. And this is, you are right on there, Olivia, with what we'll be saying with this. But think about that. If you don't reject the null, it means you failed to reject it. Does that make sense? You either reject or don't reject. And fail to reject is just a fancy way of saying I don't reject it. Because you either will reject the null or not reject the null. Now, what word will we not use? What is the bad word in this class that we don't use? We never say accept the null. Do not say I accept the null. We don't accept the null. That's a trick on any sort of test question. When it says accept the null, I will scream if someone puts that on our test as a right answer. You'll hear me scream. You'll be like, someone's screaming. Someone put accept as a right answer on the test. We don't accept the null. Ooh, Kayla knows right there. We only reject or fail to reject the null. We don't accept it. It's just like, we'll continue to believe the null. That's failing to reject means you continue to believe it. What's your conclusion? We fail to reject the null. There is not evidence for the alternative. Ooh, good. We fail to reject the null. There is not evidence for the alternative. If you reject the null, there is. It just depends. If you reject the null, that means you do have evidence for the alternative because you're going to give up the null and say, I've got all evidence for this. If you don't reject the null, which is fail to reject, there's not evidence for the alternative. Do environmental factors cause genital abnormalities? feel like we should have rejected the null, but we didn't. Does it say use an alpha? Okay, good. Ooh, I think they added that onto the question. They're talking about alpha right there. That's the 0.05 right there. It is unknown if it causes it because we can't talk about change. Woo, I got scared. I got like one question wrong today and I got really scared. Snay right there cracking me up. Awesome work right here. Cool stuff. Good stuff on hypothesis testing. Let's hop back here to the main screen. Snay's question is next right here. Let's go to main screen here. I want to make something for test 3. It can be. Kayla's right. In our classes, it's always a trick question. If you ever want to do causation, you would need a study, like not a study, an experiment where you actually have like randomization and a control with very, very controlled studies. There's Discord for this class and we get a for yes. Vincent, email me. So we don't, well, since we have Vincent, email me and we'll make sure I get you hooked up on the Discord that you can join and get some extra credit. You can even talk fantasy football in there. You can talk sports, you can talk video games, fantasy football. You just get points for being active. Hey, if that helps students just relax and just talk to people, because we've had some people kind of meet each other there and start talking and just enjoy some time. I was able to get the 4-year models, but I'm not sure if we should be creating the models for each value 1 through 10 or if we need to experiment each one and then pick the plot, the best one. Send me your current file right here, Snay, and we'll run it and we'll kind of show what you need to get. Maybe I'll kind of point to what the right answer is. I think the right answer is pretty close to... Are you seeing maybe that? I'll show you how we get it. So send me your code right here so we can keep doing that. Oh, thank you, Kayla, helping out right there. So message me up. I just saw a message appear on Discord. I just saw it. This is why we love the Discord. Thank you, Snea, so much. Oh, and then feel free to drop that other request in the chat. Like on the Discord. Just saw that right here. No, it's so awesome with the Discord. Oh, yeah, you've got a fantasy football club trying to start up? Trevor, have you mentioned it on the Discord? Are you on the Discord, Trevor? Let me mention this on the Discord. People are validating right there and making sure they're on it. Trevor, you on the Discord? Let me see. Trevor Reeves. You mentioned you are starting a fantasy football club. Cool. I pinged you on the Discord. I got a few people who are down. Oh, then you already probably did it. Sorry. Might have already been mentioned. Joe. Okay, cool. Maybe other people will mention it too. No, that's awesome, Trevor. And that's, it's really cool. Oh, yeah. Just post on the Discord if you want, or ask me on the Discord the question. But no, awesome stuff right there. That's what we like to do. Okay. I don't want to show everything, but let's... No bad. Brian's doing fine. Not sick. This looks excellent. I see you made all your models right here. Let's go in. I'm going to run this. And let's look at these models. So how would you evaluate this? How would you evaluate this, Snail? When we look at our models right here, and probably... I would probably... I see it. Let's talk over this output right here. It's not showing too much. I mean, I think I gave you the model, so you should be good. Let's just show this. Let me clear this out. Okay, cool. Let's go look at the data right here and take a look at the models we got. Okay, let's go take a look at it. You don't need to... Yeah, let's go take a look. So you can plot a few of these. Maybe plot your best ones. If you feel like your output... Everything's fine. Everything's fine. If you feel like your output is too much, let me know. If you feel like your grader's ever mean to you, let me know. We're all about being fair. It's hard to say exactly how much output you'll need every time, but you always want to look at it and be like, if I was grading this, what would I think about this? And if you ever feel like you're graded unfairly, let me know. But I think the answer for which model we should use here should be pretty obvious. Oh no, don't dream those things. What metric on this, right? There's a lot of stuff going on right here. We got all the different Fourier models. We got the R squares. We got the R squared adjusteds. We got the sigma right here. I think the sigma it's reporting is the RMSE, which then the answer becomes kind of obvious. We got the statistic. What is that one? Got the p-value right here with the model. There, you want to talk about some p-values that are statistically significant? You want to talk about some statistically significant? These p-values are 0.0 hundreds of zeros. No. The log likelihood, I don't use that one that much. I'm not a big fan of log likelihood. But with these metrics right here that we're reporting, so what's your feel on this, right? Like, what's your take on this, Snea? What would you talk to someone about this and say, well, like, you know what, we should probably use this. And you know what's very interesting? Kayla with 201, all we're doing is adding more X's right here. Snea, you did it perfectly. That's the exact right answer. What happens in a decision tree when you split a decision tree further? So this goes to like the idea of decision trees, that if you keep splitting a decision tree, if you keep adding X's, which is what we're doing right here, we're adding more harmonic terms to this, which are the ability for a wave to be tighter. Like we're doing waveform fitting through this. Like we're fitting curves like cosine and sine curves to this. Well, the terms will be less and less significant, correct? But what happens to R squared as we keep adding in terms to a model? If you keep adding in terms to a model, R squared will do this. Like if you keep adding in X's, and so Snea's on the right, because it's going to, the more X's we add in, R squared will always go up. So the way we counterbalance that is we have something called R squared adjusted. So this is a different type of R squared, and it's adjusted, correct? Yep. So R squared will always go up, but R squared adjusts. So you want to see something really, really crazy right here. If I make a model predicting the values 1 through 100, so let's say we make a model predicting 1 through 100 from random normal 100 numbers, plus random normal 100 numbers. We're going to add in a whole bunch of terms right here. So this is a whole bunch. It should work. Cool. So here's my model right here. And I want you to look at the R squared. The R squared is very tiny. But look at the R squared adjusted. The R squared adjusted is actually what right now? The R squared adjusted is actually negative. And so the R squared adjusted is a much, and this is always going to be random. We could get a decent R squared, but R squared adjusted is penalized and will always be smaller. Does that make sense right there? A good concept that R squared adjusted is a penalized. Oh, did it only add that one random normal set? Huh. Well, it's only adding my one random normal. That's weird. Well, they'll only put the one random normals in there. Don't know why it's not doing that. Nice job, Muhammad. Another 100 points right there. So the R squared adjusted can be negative. It's a penalized R squared. I wanted it to add more in. I could go through and make other X's. But when you do this right here, we do not use R squared to compare models. Why? Why do we not use R squared to compare models? Good concept right here. Why would we not use R squared to compare models? Going right here, let's make a model where we predict the horsepower of a car from all the variables in the MT cars data frame. So here is a model predicting the horsepower of a car from all the variables. But let's take the horsepower of a car predicted from the miles, or this right here, and let's make a different model. Why would we not use R squared? Because what would always win if we used R squared? What would always win out if we use R squared? Which, oh, wait, no, it's the same model. What would always win out if we used R squared? Exactly. Snea is saying it perfectly, that R squared adjusted is adjusted for how many variables in the model. And notice this one has a bigger what between the two. Going from this R squared to this R squared, there's a bigger what because there's more what's. And so Snea is on the right track with this. Why is there a bigger difference between this R squared adjusted, this R squared, and this R squared adjusted? Because there's more what's in this model right here. And then I'm going to go back to the main topic again. Because Snea, right, the answer is 7. The answer is 7 to the which one we use. And then I'd probably show that. Not more residuals, more X's. More X's. These are the X's right here trying to explain the Y variable. We're trying to explain the horsepower of a car, and we're using what was the miles per gallon, what was the cylinders, the disp, I don't know what that is. We're using all these different variables right here. There's more X's right there. So with more X's, it's going to get penalized more, and we see a bigger difference. And then notice down here, we're using a 1X model, which is called simple regression. So when you get all this output right here, it looks like a lot. It's like, oh my gosh, what are we showing? And when you see all this output right here, your eyes should go right to here and say, okay, my best R squared adjusted is at 7 degree like Fourier terms, which are how much we're allowing the waveform to get smaller and smaller. Exactly, Snay. It goes back to these concepts. I tell people it builds even from 201. And with this right here, this is going to be where I would go. Also, the sigma is how much our model misses by. I'm pretty sure this is RMSE or of some sort. And the smallest miss our model makes is on 7. The answer is definitely 7. Statistical significance, everything is ridiculously significant. Like you're able to talk about this. And what we're trying to do right here is we're trying to fit waves, the easiest model to see. I think you might have graphed some of these. We might look. The easiest model to see right here would be the one wave. So doing a 1 degree Fourier term would graph one sort of waveform through this one sort of sine curve. And then when you go up to the second Fourier term, it's going to take a higher degree, like a higher frequency, I should say, a higher frequency waveform, and then composite these together. We've got really good notes on these, but it composites this into one wave. So you can think about this pattern of data as a composite of different waves. Really impressive, and a lot of companies use it. I will show one more thing on this, and we're gonna hop back to 201 is next questions right here. If I can show some of these graphs, because I think you have some of them graphed. Super awesome stuff. Oh no, 2 seconds, we're gonna show it graphed again. People cracking me up in the chat right there. Also stuff. And the answer is most definitely to the question. I just saw the question there. Most definitely. All right. Yep. I say yep a lot with exclamation point. I'd be honored to. Awesome stuff right there. And you do have, I see, so you're plotting it. Let me look at the Gini plots. I love the glance function. Great stuff right there. I graph the observed versus the fitted. That's what we need to do, right? Yep. It's just that, and I think a lot of times, let me see your graph. Here's the Gini plot. You could graph, and you got the residuals going right here. Oh, are the residuals working for you? Residuals should be plotting. It's not giving me any residuals when I run your residuals. But we should be able to graph. So we should be able to fit this. I like to look at the model. You're looking at the fitted versus the actual plots right here. And yeah. Oh, you've saved as plot 2, and then because you were Gini plotting it. There you go, I see it. That's a good way of looking at it. You might take and just do a plot of the model itself. So we should be able to do this. I might come back, Snay. I might, let's try this real quick. Write a real quick code right here, and then we can do some more 201. You've got your fits. I'm going to bring this down here. I'll show you what I might want to see. I love looking at these models. So I'm only going to fit the first Fourier model. And that's fit now. I've deleted down your code to the first Fourier model. And you've got it stored into the Fourier gas. And so now we need to make a forecast. And there's the forecast on it. And so I always love, his book is so exact in doing this. Because now we need to combine things together. Let me go and make sure I do it exactly the way. We're going to show the screen here in a second again. I'll probably show some of this code right here. But you have to be very exact on how you add these things together. And so we're going to show this here in a second. We're going to get an exact plot right here. The way these things are put together are just very exact. No more errors. All the errors. It's the auto layer. Auto layer sometimes gets me. Okay, here we go. Let's get this going. Exciting stuff as we have it all off the screen. There's the fit. Got the fit. Get the auto layer. Take the variable and plot the fit. Okay. So we get the forecast. I'm showing it here in 2 seconds. Store the forecast. Take the original data. The Y variable of interest is the barrels. Please work today. And we've done it. Let's show it. So Snay, you might want to show one of the things like this. But right here, you can see the harmonic regression. So I wanted to show a little bit of the harmonic. But plots like this, it's the auto layer, and it catches me off guard. I'm trying to get my syntax down for this code too. Sometimes you got to go to the book, but I'll be like, where's that thing? Let me grab that code. And so we need to save our forecast, and we could increase. Let me end the chunk here, not there. Let me end the chunk there so it doesn't go down any further. But you could shake, and this is what harmonic regression is. Like I said, we're fitting this waveform, which allows for more oscillation. We should be getting higher waveforms. We should, maybe the second degree waveform. There we go, there's our higher degree waveforms. But does this make sense to everybody who's in 475, Sneh and Mohammed, that we are increasing, and we can see the predictions right here, and as we increase a composite of either like one wave, there's one wave going through, and then we go to a higher frequency to fit the second wave through. I don't really see the second wave much through there. You could, I would fit the best model probably. And there's the third wave going through, making a composite. Fourth wave, and every time you see this, you'll start to see more oscillation in the data going higher. And we'd want to fit up to the 7th degree harmonic term, which is going to allow for higher oscillation. And what's really great about all this, once again, is we should be able to go here and go to GG title and say, or we could do labs maybe. I'll just check my title. And then I'm going to show you something super cool, Sneh. There's a library, my last comment on this is library called GG Easy. And so GG Easy has function called, where is it? Easy, there it is. Easy center title. And watch this. Oh, I didn't do a plus. Easy center title, guess what it does? The whole point of that code right there, I just found it like last week or something. The whole point of the easy center title is it's one argument with nothing inside of it that just centers your title right there. So it's a good bit of code. You have to like change the what is it called? Can't think the theme. You have to change the theme and all these different things to change where the centering is. But someone wrote a function that just centers your title. That doesn't take any arguments. Just it's in library GG Easy. Yeah, super easy to center the text. Now it's like, oh, just run a easy center title. It's like, there you go. It does all the background work for you of running whatever function it's running of centering the title. You see it's changing text, doing all these things. It just runs that and fixes it. So cool. Love it. Love it. Really great right there. So really cool stuff. Maybe throw a title on this. You know how to change labs and stuff like that at this point. But yeah, and look what we get. Back to Stat Tool 1 right here. Stat Tool 1, I want to hear it. What do you think we have for any sort of predictions we make? If we have a forecast right here, what would we be giving for that forecast? What do you think we'd be giving for that forecast right here? We'd be giving a what for our forecast? Ah, yes, let's do that here because we are back to Stat Tool 1, and anytime we give this forecast, we'd be making some confidence intervals. Let's go do it. So we are back to Stat Tool 1, doing some confidence intervals here. It really all goes full circle to where we're doing Stat Tool 1 confidence intervals. I think, Brianna, you are right. The question was nice. Thank you so much, Kayla, right there. Huge props. Pretty sure you're right. It's, yep, Brianna, then Tiffany, then Trevor, then Mohammed. We should have enough time. We're trying to go through all of them. The hardest things in 475 for me right now is a lot of these packages are new to me. So sometimes the code is the hardest part. The theory is very important. Like, I know the theory inside and out, but sometimes that code just fights you. Sometimes the code's like, I'm not going to do, and you're like, well, maybe I've got an error in my code. So the theory is sometimes the easier part. You got to know the theory and the code. So I know the theory, I just got to get my code down. That's why I go to the book and I say, what does the book say to do here? Because the book's always going to have the right way of doing stuff. Unless it has the wrong way. When I look in his images and not being displayed the same way, I run the code and I'm like, why is the code not doing my thing? Oh, great work. Nutrition Lab. Guess what? It's time for the Nutrition Lab 201. Let's go check it out. So we've got here a Nutrition Lab is testing hot dogs. And we are going to take a sample size of 60. Me too sometimes. Like when it doesn't do exactly what you want. So can anyone tell me any of the notation for this problem? Any of the notation? What is any of the notation right here? Any of the notation? We'll mark some stuff right here. We need all of this notation. The more notation we have, the better. Ah, we did, yep. Practice, practice, practice. And And we have here, N is 60, exactly. That's the sample size. Standard deviation is 35. No, we could find standard error. I can find that here in a moment. And degrees of freedom is 59. Great job, Gianna. Everybody, 100 points. I love visualizing stuff. That's like the best thing, like making graphics. It's like, I gotta design that graphics. Cool stuff. And then Y bar is the sample mean of 312. So we need to go down and enter in these numbers. The standard error right here. Can anyone calculate standard error real quick for me? It's S over square root of N. I'll trust you in the chat. Who has the calculation of the standard error? And we're just going to plug that into the, it's this is this. This or this. Oh, T applet, thank you so much. Oh, we need the T. Ooh, we got to put the T up here. The T with 59 degrees of freedom for, my gosh, perfect job right there. And the T, should be a quote too. The T is, I think, I'll show you how this is found in a second right here. We did it earlier, so I think it's still in my head. So with this right here, oh, you're drawing off here, yes, that's why you can't calculate that. Here, I'll go and do it real quick. I'll solve it. I'm here to teach. That's what I do. And so 60 square root 35 divided by this, 4.5, 4.5, 1, and 85. Actually, right there. Okay, so now, how did we get the T? And so Kayla did an amazing job right there, putting the T applet in the chat. We need to know the degrees of freedom whenever we're doing a T calculation. So we go in here and we say there was 59 degrees of freedom because the sample size minus 1 is the degrees of freedom for a 1 sample T. And, oh, so it was, it's 59, sorry. So up, and there it is. We're going 95% confidence. I like to shade the middle. I was talking to my nephew Tolliver yesterday, and he was going a little crazy. He's 6. He turned 6 soon. He was being a little. He was being a 6-year-old. He's 6. He'll be a 6-year-old sometimes. A lot of the time. And so right here, we're going to plug in those numbers. That's how we get the T of 2.001. And let's plug in these numbers now. Sorry, Tolliver. I'm talking about you. Says, Uncle Brian, why are you making fun of me on your stream? So how do you know about the internet? I can't imagine. When I was a kid, we would talk about the internet like the internet is a place. Like, and then the internet was like coming about. I mean, the internet's been around for longer than I've been alive, but you know, rose to prominence as I was like younger in the 90s. That's when you see people getting on like AOL, and you got bulletin board services and all that stuff. That's when you see the internet like rising up. And so now we're just going to solve this right here. We're going to solve this out. So like seeing like the rise of the internet, like people being like, oh, I'm on AOL Instant Messenger. If you know about some AOL Instant Messenger, then you know what I'm talking about. Because that's when the internet started. Not really. What did I just find right here by timesing these two numbers together? By timesing those two numbers together, which I times 4.58 times 2, what is this number down here at the bottom of the screen? By timesing this number and this number, which multiplies, or timesing 4.5 by 2 basically, because that's what this is, what have we just found? You're older than Google. Yeah, I know, right? What did we just find right here on the bottom of the screen? Because it's... Oh, and it's so nice. It's 9.04. What did we just find? 9.04 is the what for this interval? The margin of error, because it's everything after the plus or minus. So now what we're going to do is we're just going to rewrite this interval. So we're going to rewrite this interval right now using our margin of error. And we're going to do 312 plus or minus 9.04. Keep that on the screen right here, and let's go in here. And we're going to bring the calculator, because I made a mistake on this during one office hours. I didn't add things correctly. So there's the plus. We're just going to copy paste down to 1 decimal. Oh, it's so nice. It's just 9 if you go to 1 decimal. That makes life easy. 312 minus 9.04, and that should be 303. That should be correct. Mine, I got lucky on the decimals. This rounds on 1 decimal to 312 plus or minus 9. So double check your work. It's always lower than upper. So that is how we solve this on the screen right here. Follow through, check your math, and find the T. Not use a Z. Do not use a Z. Z will get the wrong answer. What assumptions have we made? We have made the assumption that they are independent, which basically means random, and they are normal. There's the nearly normal. Is the randomization condition met? We don't really know, but probably. Not my favorite question. Is the 10% condition satisfied? Yeah, these are definitely less than 10% of all hot dogs. Remember, the 10% condition is sample less than 10%. Is the nearly normal condition met? We don't really know this one either, but by way of large enough, we probably have a large enough sample. So I'd assume the sample size here is probably large enough, unless it's extremely, extremely, extremely skewed. We're probably large enough, so we're probably okay. And then the last part right here, I am 95% confident the true mean sodium content of these hot dogs is contained in the interval blank to blank. The closest one to that is we are 95% confident the interval contains the true mean sodium content of these reduced fat hot dogs. And I think we've done it. There we go. Chair's just squeaking away here. With that, let's hop back to the main screen and start another problem. What should let's do? I don't click this one nearly enough. Wake up! Wake up! Let's see right here. Brianna had the question, and then the next question was Tiffany. Tiffany has the question right here. Chapter 16, a random poll of 700 workers. You got it. Tiffany, thank you so much, and everybody, thank you so much. We're almost a bit more questions if you have it. Kayla, you are a rock star. Like, you have earned the rock star title. That's a huge help. I really appreciate it. I scrolled through the chat right there and just double checking. Big help right there. Like we say, Vols help Vols, and we're all here to help each other. And Kayla, thank you so much for your activity on the Discord. Means a lot to me that people are joining up. So it's chapter 16, right? Oh my gosh, chapter 16. What? Chapter 16. Getting close to the end. Like, there's only two more quizzes after this. You're gonna have it all done. Kayla, you get it all done before like Thanksgiving. You'll have it all done like next week. Be like, I'm done with those my Pearson things. Just got to review. Just got to keep it in my head now. Let's go find that. This one's all about tests and power. So here we go. Ooh, we got a confidence roll. Let's go check it out. This is a great one for today's stuff. So this here is almost the chapters we're doing. The ones we did last night. Let's go check it out. Here we go. Chapter 16 quiz. Poll of 900 working men. That's the goal. Do it. Make those goals happen. So construct a 95% confidence roll for the true proportion. At this point, you want to go grab the formula. As soon as I hear construct a 95% confidence roll for the true proportion, I'm going and grabbing that formula. So the formula is p hat, because we're doing proportions, not means this time, not means. Trevor, you swing by any time. You'll see like other Kayla in here. We got 2 Kaylas. They'll swing by to say hey, and they're not taking any classes right now. You can swing back by. Your points will be reset, but I can upgrade you to meme tier level. We've got meme tier for the top level that is like beyond the points. So you can be like, hey, Brown, put me at meme tier level. I'm not in your classes anymore. And you swing by and flex those points on people and be like, whoa, meme tier. People get the hang of my class, but when they're the first week, they're like, what the heck is this? Lucy, good to see you. Feel free to ask some questions. We're about to open questions again. We got another 30 minutes or so, but drop a question in the chat. So good to see you, Lucy. And I've had so many students for so many times. It's just awesome. I love seeing students progress through, and I love students swinging back by. Yep, great stuff. And so here's the equation we're using. What do you think we should identify? You know what we're going to do. We got the practice down on these. What do you think we need to know? What do you think we need to know? Let's start marking our notation. Let's do this. Oh, this one's a really good one. That's a great review question. Review. I think that's everything we need. And what do we have? What do we have here? Who knows any of these? And great job right there. That's the sample size. Sample size? Give me one more and I'll solve the rest. That's not Z, but it's going to be used to be found. One more. One more. Very famous number in statistics. When we build 95% confidence, you might know that one. Great job, Tiffany. Tiffany, you're just here making sure we get to... Oh, I'm going to drop my pen. Practice all the questions. Extend long bit to help on videos for... Yes. Let's do it. Which one, Lucy? Mention that. I think we do have just enough time to get to it. We'll get to it here. Mention which question you want me to talk through and work through, and I will do that. I'll make sure that's in this video. You don't have to say either. Don't worry. Like, thank you for swinging by and asking the question. Try to work through these not too quickly. Oh, and this time we won't be going to T, though. Because remember, this is not Mr. T. This is not a mean one. This is a Z, so we won't be going to T. We went to T today. But to this problem right here, we're going to go to the mean. Excuse me, we're going to go to the Z-score. Oh, you found Trevor, 100 points. MuBot knows all. The reason is because we're using Z right here. We're not doing means. So Z goes with P, T goes with means. Mr. T is mean is the way to remember it. He's a nice guy, but if you're doing drugs, he'll be pretty mean. I'm sure. It says, don't do drugs. 95. Between 1.96, very famous stat number right there, 1.96 for 95% confidence. So that tells us the Z-score we are using. Because it says 95% confident, we need to cover the middle 95% of the curve. And so we do know the Z-score is 1.96. From here, the question becomes, plug the numbers in. And so let's go down here to the bottom and put in our p-hat, which is our estimate of the truth. We'll click the pen. P-hat is the estimate of the truth. Plus or minus the Z of 1.96. Square root of p-hat q-hat over n square root. Let's go solve that margin of error. Question one's great. You bet. Which thing were you wondering about, Tiffany? Mention which thing you're wondering about. I'm solving through the mathematics right now. Make sure to mark your notation, have the equation, and then the Z-score is found by finding the middle area of the curve shaded. Is that what you're wondering about? I don't know which thing you want me to go back to. The Z-score will be found by shading the middle area of the curve. So to shade the middle 95%, is going between a Z-score of negative 1.96 to 1.96. Hence, that's the Z-score we're using here for 95% confidence. If it says something like 90, okay, awesome. If you say 90, it's going to change. Or if you say 99, it's going to change. So this will dictate the Z-score we use right here for this equation right here, this equation that we're using. Let's go ahead and solve out the question. Go down here. I always solve for my standard error first. So I'm just solving the standard error right here. Divide that by 900, square root it. And so this is basically 1%. So we're going to get, okay. And then we're going to times that by 1.96. We have now just found the margin of error. So we're going to put this over here and go to the EpiPen. I do like that I can then keep these things on the screen. Here is the interval being solved, 0.09 plus or minus 0.0187 rounded up. And now all we're going to do is just add and subtract to put these numbers in. 0.09 plus 0.0187. That's the upper portion of the interval, and it rounds up to this. And then we take and we just subtract 0.09 minus 0.0187. And that's the lower. And is that to 3 decimals? 1, 2, 3. There's the 3 decimals. What does this constable say about the pundit's hypothesis? Because 95%... Oh, no, they predicted 6%. Because 6% is not in the interval. Let me close it off. Because 6% is not in the interval, we do have strong evidence. We have strong evidence that more than 6% of workers have a second job. So let me just kind of mention briefly right here. What are we actually doing to the value of 6% because it's not in the interval? Think of a 6-letter word, which means that you're throwing it away. You could say this, I wish they said this, I what the value of 6% because it's not in the interval. It's going to a concept that with confidence intervals, we can actually do a statistical test. And what are you doing to the value of 6% because it's not in the interval? That's the concept to be learned right here at the very end of this, is that the confidence interval can actually run a statistical test, and we would what the value of 6% with the statistical test. You got it right there, Kayla. We're rejecting it. So I wish they used that language down here on the bottom to say we reject and so then we have evidence for alternatives. So let's just write that here real quick. what we're actually doing is we're actually running the statistical test of the true proportion of men with a job is equal to 6%. And then we're looking for evidence that the true proportion of men with a second job is greater than 6%. So at this point, we would reject the null, and we would have evidence for the alternative. And does that make sense right here? Like, this interval is evidence. We never accept. Yeah, Lucy, no, see, we were talking about that earlier. You reject the null, and then you have evidence for the alternative, or you do not reject the null and you don't have evidence for alternative. So the interval right here shows us that 6% does not look to be a viable value, because we think the truth is somewhere between 7.1 to 10.9%. So we would reject the idea of 6% and say we have evidence, like they're saying strong evidence, and evidence is always connected to the alternative. So good stuff right there. Lucy is like old school here with some quote 3 right there. And that's got it. I think let's remember the next one. Vols help Vols. Love it. Love it. Let's hop in here. And thank you so much. Once again, I try to get to as many questions as quickly as I can. And sometimes I'm like, I'm just going to break. Chapter 14, flight questions. You bet. Of course. Let's go check it out. Chances you leave on time with the histograms. Here we go. Rolling on through. Everyone giving me so much power right here with all those great answers. Wilson and Lucy in the chat. I love it. Wilson's got, do you know Wilson? He's got that Mike Tyson punch out screen up right there between the scenes. I don't think I have that in the audio anymore. Oh, I got them gone. I used to have Pokemon on my audio. Which thing is right on my Pearson? Can you check and make sure that which thing is right? Hey, what's up, David? Good to see you here. You're former student, right, David? I see names. I'm like, which thing? I don't know which thing to check. And good to see you here, David. Let's throw out 100 points for David appearing in the chat. We're going to get the next question loaded up right here. The next question is the flight questions from chapter 14. It's like your flight leaving on time. And I feel like I should have done, like, you ever see those ASMR channels where they're like, hi, welcome to our channel. We're going to tap on the microphone. So weird channels. Here we go. Let's just do that. It's my new job. Oh, it is first class? I'll take those 100 points. Well, there you go. You got them right there. Can you do some lab 8? You bet. You bet. We'll be doing that here soon. I think we have Muhammad's question next, then Lucy's. I think that's the order. And should be able to do this. Here we go. We got this. We might do this one a little bit quicker. We got this, though. We got this. Here we go. I think got the flights leaving on time. Let's hop into it. Let's do it. So here we are with the flights. Oh, did I not check my answer? Oh, did I not click check? Sorry, Tiffany. It's gone now. It should be right. It should be right. I don't know why I didn't check it, but should be right. Tell me if you have any issues. Should be right. Okay. What are our assumptions for intervals? Condition 1. Condition 1 is that we have a random sample. Condition 1 is that we have a random sample. So we randomly sample these flights. Did we randomly sample it? I think we did. Sure. Random is basically independent. If they're random, they're independent. They separate these sometimes. I don't like that they do that. Yeah, we'll be doing it. Question 1. Yep. I'll be doing question 1 here, Lucy. Definitely. We should be getting that soonish. Are these 72 flights less than 10% of all flights? Most definitely. Does this look about normal to you? Now, the sample size here is 72. So this would have to be ridiculously skewed for us not to meet the condition. So remember, the larger the sample size, the more skewed it can be. It says 40 to 50. It can be extremely skewed. We have a sample size of 72. So do you think we pass the nearly normal, which unless this was like ridiculously skewed, which the notes don't even talk about, which that doesn't even look kind of skewed. It looks very good. I think we might have just enough time, Tiffany. That's going to be kind of close. But no, thank you, everybody. And remember, we will be back for more office hours tomorrow and class later today. So I think we're good on that. This is not ridiculously skewed. The notes don't even mention ridiculously skewed. But once again, the more skewed it is, the larger n needs to be. And this is passing the nearly normal by way of large enough n. Large enough n is now part of the nearly normal condition, which is condition 3 for quantitative data. Since we're doing the mean right here, we need to be doing quantitative data. This is this is Mr. T again. What's up? This is a confidence interval for the true mean. So we have the third condition being nearly normal, which is how we talk about like the way we do it right here. So anyways, we have here a 90% confidence interval. Let's go ahead and start marking our notation. And this is where people are going to make a mistake. We're not going to use z-scores. Do not use z-scores. Do not use z-scores. We are going to go here and use y bar plus or minus t with n minus 1 degrees of freedom. That tells us which t we are using because there's just infinite amounts of t's. S over square root of n. This whole thing right here is the standard error, the s over square root of n. So you notice it gives you notation. We literally have the mean. We literally have the standard deviation. The only thing we're missing right now is the degrees of freedom in the t. What are the degrees of freedom for this problem? What are the degrees of freedom? Like mathematically, what are they? Like, well, not like notation-wise, because that's on the screen, but what would be the degrees of freedom? The degrees of freedom would be the what, right? Would be what right now mathematically? Like, solve the degrees of freedom for this problem for me. Like, what mathematically is it? 71, Trevor, amazing work, Trevor. 100 points in the chat, Trevor. 71, Kayla, also great job right there. We have right here 71 degrees of freedom. Exactly, Kayla showing the math right there. 72 minus 1. And so now we go in here and we say, okay, we want 71 degrees of freedom, because that's the degrees of freedom right there. And then we want to do 90% confidence. And this is the t statistic. Now, this is not the z. It's very close to it. But it's 1.667. So that's going to tell us the t we are going to use, 1.667. So the t, we'll put blue in notation up here. T is equal to 1.6, and that's usually where people can't find the number. Now it becomes a plug-and-play problem of 80.9167. Oh, not times yet. What you doing? Plus or minus the t, which is 1.667. Gonna start to go over. And the standard, I love that they put all these decimals. I mean, wow, you needed that 6 on the end right there, didn't you? And then 72 is the sample size. We square root that right here. So good stuff right there. Let's go ahead and solve this. Make sure to be very careful putting in the calculator. I usually square root the 72 first to get the bottom. I copy that to go 3.14006, square root, and now I know I've found the standard error. That is the standard error. I times by 1.667, which was the t, to get the margin of error. So now this can be rewritten right here. We're going to rewrite our equation as 80.9167 plus or minus 0.61, and then that's going to round to 7 right there. Gotta love those decimals. Only to 2 decimals, so we should be good on our carrying of decimals. We're going to leave this right here, and we've got it written on the screen so we can see it. All we're doing is adding and subtracting these numbers. Thank you, Kayla. Kayla, 500 points again. You're solving this along with me. You're practicing. That's what we want. And you're helping me check my work, which is even better because I do make errors. It will happen every once in a millennium or more often. So Kayla's answer is perfect right there. Great answer, Kayla. And then let's check the other one. We're double checking. Always great to have someone double check your work with you. And the other answer is 80.30. Perfect answers, Kayla. So Kayla is 100% correct. I had no doubt in my mind, but I'm just showing it. I really didn't doubt it. I was like, you got this. And you solved it right along. Yep. So that's the answers right there. And then what does this interval mean? We are 90% confident that the true mean percent of flights. And so it's weird because this is dealing with percentages, but it's not a proportion. It's like saying each month. It is quantitative because it's like what percent, like it's a quantitative amount, but we're not asking about individual flights. This question is a little bit weird theoretically because this is the percent for a certain month of the flights on time. And we can be 90% confident the interval contains that 90%, no. 90% confident the interval contains the true mean monthly flights. Yeah, a little bit change word. There's 90% chance that true mean monthly percent. No, it's 90% confident. If they were to change that on me, I'd be pretty. No. I think we have 2 more lined up. I think we have Muhammad's question. We'll mention that kind of here. And so Muhammad was wondering about, and I think Lucy's is next because we might jump the line on that one. Make sure we get a little 474 in here. 474, yep. And Muhammad's question was, let me hop to the main screen while we get this going. Excellent work, everybody. Teamwork here. We're all here to help each other out. Muhammad's question was, I'm scrolling through the chat. Generate the residual plot using the GG residual for part B. Okay, let's go check out some GG residuals. Kayla, you are a rock star, and I truly mean that. I realize I'll just look Kayla out. Awesome, Trevor. Thank you so much. And great work there, Trevor. Not the easiest of problems. Like none of these problems are like super duper easy. They're all going to come down to practice. They're all going to come down to like, can you identify that notation? And once you get the notation, can you then do the mathematics? A lot of it's notation. Okay. So let's talk about how to get our residual plot. And let's do this. Here we go, getting residual plots. And let's look at a residual plot. Wait a minute. Ooh, I'm trying to clear this out. Okay. Let's go look at some residual plots. So what's the deal with residual plots? Now, I've already got the time series linear model saved in. Thank you. I'm using a little bit more here so we can jump into this because we've only got 27 minutes till class. So we've got a model right here. So we've got a time series linear model predicting the January electricity use, I think in Victoria or something, Australia. So here's our model right here. So it's just saved as a model. This is a Mabel. So it's a table of models. So it's a Mabel. We could make more. You can make multiple different models in here. Of course. Yeah, this 7 would be great. Great way to end the week. I get the following example of the book. Usually must be used for a Mabel. So it looks like, so Muhammad right here, your Mabel must have more things. Run your Mabel. So Muhammad, I want you to, awesome, Lucy, we'll do it next year. We'll do 474 part 1 of activity. When you run your Mabel right here, do you see more than one Mabel? It sounds to me, when you run it right here, you're probably seeing more than one. You might be able to, let me try something weird. I bet you, if we were to go here and add in an extra Mabel, and okay, that looks to have run. Okay. There might be a way to do this. Let me clear my code and I've added in a second model. Let's take a look. You only see one. You might need to send me the code. So here, we might run into problems right now. I've made 2 Mabels right now. So you should only see, and does it say, it should say Mabel right here. It should say Mabel. You should only see time series, but I added a naive to it. So I've got my naive model on here. And so with this, see, mine's a 1 by 2. And does it say Mabel right here? Send it to me on Discord. Okay, let me take a look. Because I'm wondering, yes, you could do this. Ooh. See, it's mad about it. It's really mad. Yeah, so this is, let me fix it. Because I purposely changed it to make this happen. I'm removing out that naive model I added. And then let's go back down to here. So that's probably might be what you're, error. And so now we're back down to this. Hey, there we go. So let me take a look right here. Let me go grab that on Discord. Go grabbing that code on Discord. Awesome. Grabbing the code, dropping it in. Errors. So it looks like you can't subset those off. I did look at where your Mabels are created. Well, you got it right there. You've got a view on or something. Take off the view. That might cause, on line 27, you've got a view, Muhammad. Probably remove the view. Like, it's good to view stuff. Let me grab Discord. And then, this looks like it should work. The answer is you might just need to rerun the code. It's chunking away right now. Give me a second. I'm going to show. Whoa. Whoa. Something. I'll show it. Oh, you don't have a subset right now. Double check. Here, let me show you, Muhammad. I'm going to run this all. I'm going to put a chunk below here. You don't have to do this, but I'm going to run all your code by running this. Does this make sense? Let me do the following. 2 seconds. I'm going to clear everything out. I think you don't have the subset going. Clearing plots is taking a moment. Like, no joke. It's actually like saying clearing plots, and it's taking a moment because that plot's taking up a lot of memory. So a good way to make sure everything you have is in the right order. I'm going to send an announcement class here. So I think there's a problem where you're not subsetting right now, because I'm going to run all the code. So just so I don't show everything, I'm going to run all the code right here. I think you're not subsetting just January. Right now, you're Jan 14th, Vic elect. But you're passing that's not the fit, is it? You're storing Vic elect. Oh, okay, here's the issue. Okay, I see the issue. On line 35, and so I'm getting a lot of this right here is the full everything. That's not just the Jan 14th. On line 35, ooh, let me show you this. I need to show this. There's an issue up here on the code. So I'm gonna show you this one code right here. This code right here. Look at what's going on with this right here. Don't worry, we're gonna fix this. What you're doing is you're storing in both ways. You've got to store to the right, you've got to store to the left. So we want to pass through. I think I basically show this, so I'll show it. We want to take this data right here and pass that through. And so let me clear everything out. I need to clear the environment and run the code above, run the current code, and that gives the fit right there. So we should have the fit saved. So with the fit saved, we should be able to pass the fit. There we go. Okay. Do you see it? Mm-hmm. Now that we can pass the fit through. Just a little bit. If you know some Stat 201 residuals, looks like it looks pretty good. A little worried about this right here. That might be a little bit. If you know 340 process control also comes into play. But Kayla, this is residuals, which we've seen before. How far are our predictions off on predicting the electricity? And you can see right these 2 days right here, we were very under. We had a very negative residual. So the idea of residuals do not go away. Like, how much did we miss by? We'd like our residuals to be close to zero, and we don't want there to be a pattern in the residuals. So this would tell us if there's any sort of correlation among our residuals, and you want your residuals to follow a normal pattern right here. And so I absolutely love, but the question always in our mind is, can we ggplot this? So can we? Oh, that's a bummer. Can't ggplot it. But all that good stuff right there. Yeah, it looks like it was storing left and right. So that's the fix on it. Good stuff. We're going to hop to Lucy's question. Let me send out an email to the class, though. We're going to go for probably 10 more minutes here. We're going to go to Lucy's question. Some 474. I'm going to send out the email to the class because they're going to be taught in here in 20 minutes. Thank you to everybody. Got to look at those. Christmas break is going to be so nice. I didn't name both these classes. I've been better about keeping up with the titles on videos. Got to title these videos later tonight. 2 seconds, I'm going to title this video what's on my mind. Confidence intervals for true. There's that. And message the class. Class in 18 minutes. Big bonus. See you soon. Click here. I used to not send announcements, and then less people would come to class. And I was like, well, I'll send an announcement for every class. Gotta get the people to class. Oh, didn't send it yet. I've done that where I forget to send the announcement. Okay, that's ready to go. Yeah, rule of 7, Muhammad. Yep. It might have some sort of rule of 7 violation. 7 points above or below the mean is not what we would expect to see by random chance. So yeah, but if you look too hard at those rules, you will see things sometimes. So maybe it has a rule of 7 violation, maybe it doesn't. maybe. It kind of looks like it. It looks like there's 7 points above the mean. So I'm starting to think it kind of does. But once again, if you look too hard at the rules, you'll see something eventually. So you want to be careful how many rules you check, because 5% of rules would be broken by random chance. So if you check 20 rules, you'd expect at least one rule to be broken. So if you look hard enough, you will find a rule that's broken. Like, but by random chance, because eventually you'll break a rule, because rules are possible to break by random chance. Okay, let's get the activity up for 474. So many things. Tree-based models, love it. We're going to be doing some of this tomorrow, but let's do some of it today. Why do tomorrow what we can do today? Here we go, 474, tree-based models activity. Let's start this off. Okay, so really great start here to some tree-based activities, and 201 knows this as decision trees. So we got a bunch of packages that you should have loaded in. I think I have them all loaded in. Reg class, of course I have reg class. That's regression class. R part is for making trees. It's R part, parting data. And we're good on that. Random forest to make random forests. GBM is genetically gradient boosted, not genetically. Gradient boosted models. And caret is classification, regression, training. And proc is used for the AUC ROC for PROC. So we're good. Got them all. If you don't have these, make sure to install. Why won't have some XG boost? Extreme gradient boosting. Yeah, there's some XG boost. Then we have library matrix for matrices. I don't remember what I used that one for. You can always go to a package and wonder what's inside of it by going to matrix. Go to the package and you can actually see what's inside of it. Bunch of math stuff, it looks like. Columbine right there. Good stuff. So classification partitions. So when we classify partitions, we've got here, are we classifying thing as class A or class B? And so when we look at this right here, let's see, a partition currently contains the following individuals. Class labels and the values of their predicted values are provided. And awesome. Awesome. Sorted on gender. Use the R chunk below to do any math. What is the Gini of this partition? Okay. So it's wondering about the Gini of the partition. Which one? Which one are we talking about? A partition contains the following individuals, class and labels of values, prediction values are given. Relevant subset of the data are given. And so now we look at this right here. We have people in class A, people in class B, sorted on rating, useful part B. Okay, useful part A. Here we go. Let's take this right here. And oh, I see what it is. I think we're predicting if they're male and female. And yeah. That is not as specific as I'd love it to be. Yeah. Cool. Okay. Class. Yeah, so if we're doing Gini, we're doing collect. See, it says gender right here, but we're predicting if someone is male or female, and sort of on rating useful part P, which is how we sliced it. Okay. What is the Gini? So when we calculate Gini coefficient, Gini is how we measure impurity. Impurity is going to be the best when everybody inside of a leaf is going to be of one group. So this right here would have a Gini of 0. That'd be awesome. Because now class B right here, and that is their actual gender, I believe. I'll double check some stuff right here. That's their actual gender. So now everyone in actual gender is predicted to be class B right here. Everyone over here is predicted to be class A. So you don't see any sort of mismatching of predictions. But when we look at this split right here, and this partition, let's go back in time. We want to ask ourselves, how well does it do for this? And to calculate the Gini coefficient, we can write it here on the screen. The Gini coefficient is going to be, we have two splits right here, or two groups. Let's bring out the Epic Pen. We need to take and solve out 1 minus, and this is for the first one. How impure is this? Well, this has a 1/3, let me put that in a big parentheses, 1/3 in one group, and then we add this 2/3 in another group. And that is the impurity of this. We'd love it to be all one group. So for that one right there, it's got a 1/3, 2/3 right there for class A, has a 1/3, 2/3 ratio. And so now to calculate the impurity of that one, the impurity of this one right here is 1/3, and we'd square that. And then we add to it 2/3. It's actually easier if we Because, yeah, 1/3 squared. Well, no, that was not right. 1/3 squared should be, I think I square rooted it, is 1/9. And that's 4/9, so it's 5/9. So this right here, it's easier if you just carry the decimals or do it this way. That's 1 minus 5/9 and 1 minus 5/9. All this is equal to 4/9. So this one is equal to 0.4444 repeating. That's the impurity of that one. We'd like it to be 0, but it's the 1/3, 2/3. So now let's do the impurity of the second one. The impurity of the second one right here is going to be, let's do it in blue right here. Impurity of the second one. That's a, ooh, that one's really bad. That's a 3/5, 2/5. If you look here, we have 3/5 female and 2/5 male. So 1 minus, and then we go here and go 3/5 and 2/5. And that's the impurity of this one. So it's the right there. And let's go solve it. It's just how, oops. And so now, well, 3/5 squared is 9/25. And that is 4/25. Just easier because we can square these. So that's 9/25, 4/25. That's 13/25. Which is 1 minus 13/25, which is equal to 12/25. Times that by 4, you get, that's a 0.48. And that's the impurity there. So now that we have these impurities, we need to do a weighted impurity. So now we need to figure out the impurity of the split right here. And to figure out the impurity of the split, the way it's split it, we have to do a weighted. Great job, Kayla. Excellent work. Gotta go get the oldest. Nice. Awesome. So now in black right here, I'm solving for the weighted of it. There were 5 observations in this first one, and that's 0.48. And then we no, we need to sum that. We need to just double check it. Yep, we need to add it, not multiply. We need to add it to the other one where there were 3 observations. 3 because there's 3 observations. And these formulas are provided to you. And then we divide that by 5 plus 3 because that's the sum of the total. A lot of fun. Just doing some math. That's what we do right here. And so we're basically just finding out an average for this right here. Like, what is the impurity of this split is the average of how it divides them up. And so we go here and go 5 times 0.48. I love these as test questions. 3 times 4. Add those together, divide by 8, and we're going to get a between number that's more towards the larger number there, the one with the more observations. So the impurity of the split is 0.466, which is not that good, not that good. Do we have time for one more? So if the partition was split using the rule of rating less than 3.6 and rating greater than, so that's the answer to that one. That's how we do it. And so good stuff. Good question right there. If the impurity, or if the split had been done with this right here. Okay. And so let's go down here. If the partition of the split was using the rule of a rating right here. Okay, so that's where the split would be done. What would be the Gini indices of the 2 resulting partitions as the reduction in Gini index when using this rule? If the CP value for the tree was 0.01, would this partition be split? Assuming it's the first rule added to the model. In other words, is the reduction larger than the CP? Okay, cool, right here. So when we look at this, it wasn't talking about the original Gini. Let me look at A again just to double check. Of this partition. Oh. I think it's asking about just the Gini of this right here. Oh, I made a mistake. I might even cut this part of the video. The Gini, it's just asking about the Gini of this. It's just asking about the Gini, and then these are X's. Oh, I feel like cutting this part of the video. No, Brian went way too quickly and did the question all wrong. This is the Y, these are the X's. We haven't even done a split yet. The Gini is very simple right here. It's just 1 minus 3/8 plus squared plus 5/8. My brain did not properly interpret what was going on here. It's a lot taken at the moment. And so that is going to be the Gini right there. So 9, 25, 34. 34 over 64 1 minus, and so that'd be 1 minus 1 minus, or no, it solves out to 30 over 64. And so that's the answer right there. So the answer to the first one, A, is 30 over 64. And then we're asking, would we get a better Gini coefficient if we split on a certain way? And we're showing that right down here. So that's where we actually need to start calculating out how are the A and B split up. So I'm going to do this here really quickly, just a real quick practice, then I'm going to start streaming. So if we split right here, you can see the split for B. Now we have a partition here. Do not worry about these. These are not X's. None of that matters. Rock.
It doesn't matter.
That doesn't matter, nor does this matter. It just matters that we're splitting here on this. We are splitting at this value of 3.7, which splits it right there. So now we have the first one up here is 1 minus 1 minus 1/3. Oh, is it literally going to be the way it was before? 1/3 squared plus, oh my gosh, plus 2/3. We did this one squared a second ago. Just because we already solved this earlier on, we know it's 0.444, unless I'm doing my mathematics wrong. And then the bottom one is a 1/5, 4/5 split. So this one's a 1/5, 4/5 splits. So there's the 1/5, and there's the 4/5 split. Coffee's kicking. And so this is equal to 17/25, 1 minus 17/25. And that's going to be equal to 8/25. 8/25 is equal to 0.32. Now we need to do the average of them. So we have here 0.444. Oh, Michaela, we might do it next officer. Sorry, thank you so much, Michaela, for asking. We've got class in 6 minutes. Oh my gosh. We have class here in 6 minutes. We will do it. Michaela, remind me, and we will do that next time. We'll do that right here. And I'm just solving through and showing how to solve for some Gini coefficients by hand. And it looks like, I'm trying to remember the original Gini, but it looks like, and this is going to be 5 plus 8, it looks like this is giving some sort of reduction from the original Gini coefficient, that we have a reduction of at least 0.01. It looks like this split would be done. Oh, no worries, no worries. I need to stop streaming on here so we can get the other stream going. But I made a mistake, and I realized it. I wasn't reading it properly. That's 1 point. Oh no, I need to solve it. 3 times 0.44, copy. 5 times 5 times 0.32 plus this divided by 8. There's the new Gini of 3.666. So that looks to be a reduction. I can't remember our original Gini, but it looks to be a reduction. Our original Gini was 9. Oh my gosh, my brain's breaking. I think it's a reduction. With that, we're going to head off because class is starting here soon. See you tomorrow, everybody. We will head back. More Gini coefficients to come. Solving by hand is a lot of fun. Bye for now, everyone. Bye.